Hello, I'm David Murray from the University of Strathclyde, and will be presenting our paper, Explainable NILM Networks. This work was done as part of the H2020 EcoBot project. Explainable AI and machine learning interpretability is becoming more important as more decisions are being made by computer systems with little or no human input. These models have a legal requirement in the GDPR legislation to be explainable to anyone affected by the outcome of a legal or similarly significant algorithmic decision. And as such, there is a need to be able to explain complex model operations to someone in a clear and easy to understand way under Recital 71, the right to obtain an explanation. The explanation may cover a number of approaches, such as how the decision is made, who developed the process, the data that has been used, the steps taken to ensure fairness without bias, safety and performance to ensure accuracy and reliability, finally the impact that the AI could have on the individual or wider society. This talk will be broken down into 3 steps: pre-model, in-model, and post-hoc evaluation of interpretability. Pre-model will purely address the data, its visualization, and understanding. In-model looks at the constraints on the model, as well as intrinsic interpretability, also known as transparency, which describes exactly how the model works. Post-hoc refers to any methods applied to the model output. Post-hoc also includes model-agnostic methods, such as partial dependence plots, to aid in the explanation. With regards to NILM interpretability, although the outputs may not result in legal or similarly significant outputs, the way in which NILM is likely to be used by business and displayed to customers means that any issues or incorrect statements may lead to distrust in the underlying model or the business itself, and therefore being able to explain model functionality will help to improve customer relationships. In our work, we make use of the refit dataset. This is a 2-year dataset which contains aggregate readings with submetering at an 8-second sampling frequency for 20 middle-class households in England. There are a number of challenges associated with NILM data. Bias is a major issue when initially training the network. In general, the majority of household appliances are not used for a significant period of every day. It is, for example, unlikely that a large appliance like a washing machine are actually on for more than 1% of the time over the period of a year. This means that without adjusting for this, a network trained to identify a washing machine would likely result in no predictions, as this would, over an unbalanced dataset, result in a very high accuracy. Therefore, we adjust the ratio of activations to non-activations to help ensure that the network is getting balanced training and validation samples. We have found, for example, that washing machines require around 13% of training and validation data to contain activations in order to predict the appliance consumption accurately. The refit dataset is also more noisy than some other NILM datasets, with a large number of appliances per household all contributing to the aggregate, many of which are not submetered and therefore unknown. This is challenging for machine learning, especially for being able to explain false positives. To avoid false positives and improve robustness, we include noise and additional appliance activations into the training data. This also provides us with more data to help balance the dataset. The addition of noise and random events can also aid in providing counterfactual explanations, focusing on an individual window or point, and showing the minimum amount of change needed to affect the outcome to a more positive one, or where a previously missed event is then detected. Another way that we aim to improve robustness and fairness is to ensure that the model exhibits transferability. This means that we train and validate the model on one set of data and test on another unseen set. This is important to ensure accuracy, but also generalizability, so that the model does not break when applied to data from different regions or data containing unseen appliance types within the aggregate. The examples shown are washing machines from 4 different households. We can see that although all follow the same general consumption pattern, time is a major difference between these otherwise similar appliances. In this work, we make use of an autoencoder model. An autoencoder takes human interpretable data, firstly encoding data into features, then decoding in a restricted manner. In NILM, the restricted reconstruction is the appliance signal minus the aggregate. We have used 4 encoding layers and 4 decoding layers. The encoding layers contain an in-model constraint of being causal, in that it follows the chronological order of the data, and we apply dropout to all but 2 of the last layers. The input is 2048 time steps in length, which is close to 6 hours per window to encapsulate entire appliance signals. Although few appliances are run for this long, we have found out that this improves the generalization of our models and aids in detection. Making all NILM data appear similar is challenging, and as such, we scale data between 0 and 1, where 1 represents 12,000 watts. This range is domain-specific knowledge. However, it is likely to transfer well to many houses, as they are unlikely to exceed 12,000 watts for any significant period of time. Post hoc, we arrive at the results. Although our model is trained many to many, the output is processed as many to 1. We take the center point of each window and stitch them together to create the disaggregated result window. This is done to avoid false positives at the extremes of the windows, where the network might detect an appliance as being on while the appliance's full signal is not visible. The accuracy of models can be a misleading representation of the effectiveness, and if data is supplied to the customer in a way which they find misleading, this can exacerbate issues. In this example, we look at a counterfactual explanation for why our model failed to detect the second washing machine usage in our sample window. Once the network is trained, we wanted to understand how the internal layers' activations and weights affect the outcome. Understanding this will help us to explain why the network reacts the way it does, and in cases when an appliance activation is missed, why this has happened. This slide shows a subsample of activations taken from the first encoding layer, which is the most human recognizable as the data is not yet deeply encoded. The difference between the two is that the left has been shown the complete window, and the right-hand side a masked one, where the first 75% of the window has been hidden from the network input. In this case, the data is set to 0. This window contains 2 washing machine activations, one that starts around the center and one that starts in the last 20%. We can see that the masked side has much stronger activations at the second washing machine usage in comparison to the unmasked data. In this case, our network detects the second washing machine usage when the first usage is masked. The first encoding layer halves the input length. This plot shows the difference in activations with and without the mask. We see that around the second appliance activation, which begins roughly at 1,700 samples in the original window, that the encoded receptive field, which is half the size of the original, has the biggest difference around the point 861. This tells us, at this point, the filters are detecting the second activation, but not weighted favourably. Looking at the internal weights of the filters associated with point 861, we can see the 4 weights circled contribute the least. We expect either through manual manipulation or training with targeted data that we can detect both the first and second usage of the washing machine in our original window. We adjusted the weights of these 4 filters slightly to see if the change resulted in detection for both uses of the washing machine, while not detracting from the original accurate detection of the first usage. We can see that adjusting the internal weights of the 4 filters, which represented the second washing machine usage, we can affect the model output in such a way that we have the detection on both the first and the second washing machine activation. Although this has come at a cost to the detection of the first washing machine usage accuracy, its consumption values are significantly lower. Through this work, we hope to be able to better understand the minimum change required that would be needed to detect both usages, whether that is adjusting training data or fine-tuning the network with specific samples or constraints. In conclusion, explainability is a requirement both legally and a tool to help improve performance. It is important to avoid general statements when addressing NILM on an individual feature such as sampling rate or appliance types, as the combination of these features can affect the effectiveness of a specific algorithm. Explaining features is important both for explaining how results are obtained and managing expectations. Some companies, for example, have toned down their NILM offerings with regard to commercial NILM, as there is a chance of misleading customers. In the industrial and commercial case, being able to explain the underlying process is vital, if data supplied is acted upon and found to be misleading or incorrect. We have just started to look at this field of explainable AI and hope to make contributions how to pre-process, train, and understand time series neural networks. Thank you.